Alright, so now we've seen what the response of a second order system going to look like in function of a general damping ratio, natural frequency, and you haven't talked much about gain, but and gain as well. These are the three parameters that define a second order system. However, we don't know what how to relate damping ratio or natural frequency to parameters we've been talking about in aerodynamics until now. Parameters like the Cn alpha, the aerodynamic center, or the length of the rocket, or the diameter of the rocket, the span, and everything like that. So that's what I mean by rocket parameters. The rocket parameters, I mean like the span, aspect ratio of the wings, diameter, length, Cn alpha, all this. Alright, just a disclaimer, from now on, all these videos are just stuff that I've derived, so there may be some errors, hopefully there aren't, so it's, I mean, I think it's a very interesting part of the stability. Maybe the most interesting things are going to be in the following videos. But again, yeah, there could be some errors. There's a lot of silly algebra, but just let me know if I just did something wrong. But hopefully there isn't something wrong. So okay, so we have to do some simplifications. We're gonna have to do some simplifications. You're gonna see. You're gonna see what simplification we're gonna do on the go. But first of all, the damping ratio we saw before. That damping ratio was the damping moment, and divided by the corrective moment times the moment of inertia. So this is equivalent to wait, we have to define, let's rewrite actually the equation, the angular equation again. I'm gonna write it down here. So it's a bit long, so I'm gonna do it small. So the alpha terms, Cn alpha of the fins, Cg, then the body terms, Cn alpha of the body. Oops. Okay. Let me pause and. Alright, done. Yeah, the equation is the same that we've seen before. I just split the damping, the propulsive damping. So this over here, if you recall, is just phi, the derivative of phi. I'm gonna call this I don't know, theta. I'm gonna call this beta. And by the way, phi, the derivative of phi is just the corrective moment over, yeah, we just divided everything by this, right? Yeah. And this is just, well, theta and b, if we multiply it by yeah, dynamic pressure and the reference area, it's the damping moment. Okay, because yeah, I told you I didn't use this these variables, so this is just a relation. Yeah. Okay, if we substitute here you know, phi and these variables. We're gonna have this. We're gonna have theta plus beta times dynamic pressure times A, and then we have 2 over well, phi. Cool. All right. As you can see, if we substitute here all these variables, it isn't looking good. You're gonna see that we're a bit far away of concluding, you know, what order of magnitude this could be. It's still pretty foggy what's buried inside all these variables. So we're gonna have to do some simplifications. Hopefully you agree with me with these simplifications. Again, this is all my derivations. So if there's any error or some simplifications you don't agree with, just leave a comment and we can discuss it. So let's see. Get down a bit. All right. Cool. First thing I'm going to do, I'm going to see what phi is. I'm gonna try to let's see. Well, let me just operate a bit, and you'll see what I'm gonna do with this. So phi. I'm just gonna call this phi, okay? Phi. Remember that. First of all, I'm gonna be looking at only Mach numbers that are below Mach linear. All right. So R phi for Mach numbers below Mach linear is going to be pi aspect ratio to S surface over A. And then we had the position of the aerodynamic center of the fins, the position of the center of gravity, and then we had, this is the fin term, then we had the nose cone and body term. So we had this here, length of the nose cone minus the center of gravity. Cool. All right, let's check this, the aspect ratio and the S surf. So aspect ratio is defined as the span squared over the S surf, as we saw before. So we can might as well just cancel out the S surf and just leave the span squared. And then the aspect ratio, the reference area is just pi over 4 times the diameter squared of the rocket. And then here's the first simplification. We're going to say that the position of the aerodynamic center of the fins is going to be just the length of the rocket. So remember, we're going to want to put the fins as back as possible because we're going to drag back the aerodynamic center. We're going to get the corrective moment up, which is good. We're going to get the damping up. We just need it to stabilize it. So I think it's a pretty good approximation to take the aerodynamic center to be equal to the length of the rocket. We do this first approximation. It's going to ease some stuff. And what I'm going to do is I'm going to dimensionalize everything I can, because when you have stuff non-dimensionalized, you're going to see that I'm going to drop off a lot of variables, and it's easier to see if you can eliminate any chunks of the function that are order of magnitudes lower with respect to others. So what I'm going to do is I'm going to define the non-dimensional center of gravity, which is just center of gravity underlined as the position of the center of gravity divided by L. So yeah, the center of gravity is just going to be L, which is the length of the rocket, times the non-dimensional center of gravity. So the good thing about this is that this guy over here is normally I can bound this term because it's non-dimensional. I know it's going to be something around, I don't know, 0.5 to 0.8. Something around that. You know, it's going to be between half the rocket and maybe, you know, the end of the rocket. If it's 0.8, maybe I just exaggerated, but yeah, something about that. But I can bound this term, okay? And I'm going to do the same with the length of the rocket. I'm going to non-dimensionalize it. I'm going to define the non-dimensional length. The length of the nose cone is going to be the length of the nose cone over the length of the rocket. So if we substitute all this over here, we're going to arrive to the following. Wait, I just left out one last non-dimensionalization, whatever. I'm going to non-dimensionalize the span. I'm going to call this the specific span. Okay. Specific. I'm going to define this term. Just made it up. And this is just the span over the diameter of the rocket. So we put all this into here. We will get a new expression for phi, or for phi, which is going to be equal to 2 times the length of the rocket. And then we have the specific span squared, 1 minus non-dimensional center of gravity. And then we have 0.63 non-dimensional length of the nose minus non-dimensional center of gravity. So the good thing of non-dimensionalizing is that we can compare order of magnitude. So if we take different rockets, the non-dimensional span, I know it's, you know, it's somewhere in between, I don't know, maybe 1 and 4, I don't know, 1 and 4. Length of the nose can be something, I don't know, from 0.1 to 0.3. And we discussed the center of gravity. So you can see like which are the terms that weigh more, you know, because they're non-dimensional. That's nice thing of it. And I just did like a quick analysis on, you know, if I could drop some terms, but no, you really can't generalize and say, okay, this you just can get rid of this, but get rid of this term or whatever, but you can't really. So we're just going to leave phi as this. All right, this is the simplified form of phi and non-dimensionalized. The only simplification we did here is, remember this, which isn't so bad. So cool, let's move on to the next one. Let's go. Second thing I'm gonna look into are the damping terms, so theta and beta. So you can check for yourself that theta is going to be equal to 1 over the velocity. Then we have 2, the specific span squared, length squared. Wait, actually, we could take. Give me a sec. Yeah, I can factor out some stuff. Let's do it again. factor out 2L squared over V, and then inside we have the damping term related to the fin. This is specific span squared, and then the damping term related to the body. And again here, I can't really drop any terms, so we have to leave it like this. These terms could be similar order of magnitude. So if we had the boat tail here, we could quickly see that the boat tail would be another order of magnitude in phi in this equation as well. So we could have kept it until here, but would have been in pain, so I just killed it just in time. Cool. So then beta is this. And we can simplify this to 8 over pi squared density of the air, velocity, rocket diameter squared. Alright, now comes the biggest simplification. This is going to be the spaghetti simplification. But we got to do something with it, because if not, it's going to be hard for us to simplify anything at all. So, the longitudinal moment of inertia of the rocket. What can we do? Well, we could approximate it as... First approximation would be solid cylinder and rotating about the center. Okay, that's the first simplification. Well, it's not going to be rotating about the center of the cylinder. It's going to be rotating about the center of gravity. It's not a cylinder. It's a rocket. It's not solid. It has, different densities. This is where the largest simplification is going to happen. So hopefully the longitudinal moment of inertia is dividing at inside a square root. So if we do a spaghetti simplification, hopefully it won't hurt us too much. So the longitudinal moment of inertia for a solid cylinder rotating about its center is 12th of the mass of the cylinder to L squared plus 1/4 of the mass and the radius squared. We're dealing with long rockets, long slender rockets, so we can drop this term, and we're gonna continue the simplification. We're gonna say that the mass of the rocket is just gonna be the density of the rocket times the volume of the cylinder. So basically it's just gonna be this times squared. Okay. If we substitute it here, let me talk about this. So I'm taking a density, an overall density of the whole rocket. I know this is a spaghetti approximation. I'm sorry, but believe me, this actually is going to help us. We're going to reach really interesting results with this. And although it's a really rough approximation, this is the worst approximation with difference we're doing here. We're still it's still in the acceptable limits of of being not bad enough, so the results actually we can get something out of it. So if you have any suggestions in improving this, please do let me know. So dividing, we have 48, and then we are left with, sorry, this is 48. Let me do it again. And then we have d squared, L to the third, and the rocket density. We'll call it rocket density. So I've checked like different rockets to get this order of magnitude. At first I thought it would be something like around similar to the density of aluminium, but it tends to be way lower than I thought. It's somewhere around, let me check, if I recall correctly, it's like somewhere, I remember that Stratus 2 was, I'll recheck this, but something around 650 kilogram per cubic meter. Denser rockets go up to 800 kilograms cubic meter. Some go lower, some go a bit higher, but they go around here. I'm not talking about model rockets. Model rockets will be way lower than this, because it's just hollow cardboard. But maybe model rockets will be something like 300. But in real rockets, we're going to be dealing with something around this. All right. So with all these simplifications, we can go back to here. No, sorry, we're going back to this equation. We're going to substitute, and we're going to see what we can drop. Okay. All right. So you know what? I'm just gonna. I'm not gonna go through all the algebra and taking off every variable and everything. If you want, you can. I've developed each variable here. So if you agree with me with the expansion of each of these, you can do the same and substitute here, and delete all the variables. Yeah, just remember, reference area is just pi over 4, rocket diameter, dynamic pressure is just, this is the air density, and the velocity squared. So if you start operating, you will arrive at this value of the damping ratio. Alright, I've just done the calculations once again because I wasn't too sure of the results. Just making sure. But I'll do it again. If I detect any errors, I'll just re-upload this video and see what I can do. But what I found that the damping ratio is the following. So first I put the densities like away from here. Then I multiply by this. It's specific span plus the thrust damping term. By the way, I haven't dropped any terms here. So I just substituted these equations up on the equation I showed you before. So if you try it for yourself, it should give you this. Okay. So let me know if there are any errors. I'm going to recheck again. I'm going to recheck this a couple of more times. I mean, I did it a few times, but I don't know, there's a lot of substitution and sometimes I mess up. So let me know if there are any errors here or in the hypothesis I've taken, if you think they're improvable. Anyways, order of magnitude, I've done a few checking with commercial, with Open Rocket and stuff that doesn't do the simplifications we've made. And in order of magnitude, it does actually give the damping ratio a rocket should have. Even though we simplified, the moment of inertia, we simplified the aerodynamic center of the fins. So, I mean, I'm not saying that it's very probable that there are errors here. They might be, but if I'm writing this here, I'm kind of sure this should be like this. And so dividing, we have the square root yeah, it's b squared as you can see, everything is non-dimensional, which is great because now we can bound the terms and see get an order of magnitude of what the damping ratio is. What I want to see here, the conclusion I want to get is that it's going to be hard to get damping ratios high enough such that resonance doesn't happen. Resonance doesn't happen in damping ratios maybe above 0.5. Resonance ceases, doesn't happen. Well, technically I think it's was it 1 over the square root of 2, something like that. I think technically you don't have that peak at around this damping ratio, but at around damping ratio of about a half, you already, in the body diagram, you barely have a peak here. So what I want you to see is that in practical cases, you're not going to get anywhere near this. Okay, so what I'm going to do is I'm going to what we could do, we could take real cases of rockets, substitute and see what damping ratios we get. Okay, I'm going to take 3 examples. I'm going to take the NASA Hawk, and we ran out of space. Let's see. I'm going to delete this. I'm going to take the NASA Hawk sound rocket like from the, I don't know, a pretty old sound rocket, but I just happen to have data from that. So let's put Hawk. We're going to use Rexus and Stratus 3. Okay. So, before going on, it's a good moment to discuss this term here, the propulsive damping. So, as you can see, it's going to be a bit hard to bound this term over this term. So we want to compare this over this to see if we can drop something. Well, the mass flow rate, sorry, it's very hard to bound. This can be anywhere from nearly zero in model rockets to a few kilograms per second. But the thing is, what we can see here is that there's a V dividing, because, well, in here we have V squared, so a V drops, and we have a V dividing. So this term here, I don't know, it's from 1 to 4. Let's put 1 is really, really low, but yeah, just order of magnitude. And then if we have a V dividing, V can go, I don't know, and it can go to Mach 2, 3, 5, whatever. So we're talking about V's in order of magnitude up to 1,000, 2,000, 3,000. And if we have that term dividing over here, it's going to be a large term dividing. So, and then what else? Yeah, plus the reference area. We're going to be dealing with, I don't know, something around 0.03 square meters. That's for a 20 centimeter diameter rocket. But still, facing 1,000, 5,000, this term here is going to be the division here. It's going to be pretty high. Okay. You know what? Let's do it in another way. I put the propulsive damping term over here. So this is equal to let's put mass flow rate, density of the air, pi over 4. Basically, this propulsive term is proportional to the mass flow rate over the velocity in d squared. So this term here is pretty constant in motors, kind of. Again, we're just looking for orders of magnitude. So I found this term, which relates the diameter square of the rocket and the mass flow rate, to be in SI units around 50 to 150, just comparing quite a few motors. So this is going to be around 50 to 150 over V. So if V is over this velocity, so if it's above 150 meters per second, it's gonna get, if it's below, so let's do it this way. Let's say, let's put this name, let's give this range like a name. Let's put it P damp. So it varies from rocket to rocket. Okay. So it's like this constant of proportionality, right? That relates. Actually, it's not this. I just realized. Sorry, it's 50 to 150 is not this. It's a whole set of variables except for the velocity. So this PD is somewhere around 100 to 150. All right, meters per second. So when the velocity gets over this threshold value, let's put 1 here. This, by the way, I'm trying to plot this term, so I'll just call this term, I don't know, we just use propulsive damping, so Z, whatever. So below this threshold velocity, the propulsive damping is going to be irrelevant. Okay. But then below, well, you get the idea. But I'm going to do it again. So at low velocities, propulsive damping is going to be really relevant. Okay, it's going to be larger than this value, which is going to be, well, the square of the specific span is going to be somewhere between 4 and 16, because the specific span is probably between 2 and 4, more or less. So at very low velocities, we're talking about maybe velocities even lower than, well, launch tower velocities. These velocities are pretty low. Propulsive damping is very important compared to this term, so we can't discard it. But when we have high velocities, this term just dominates over this term. So it's a pity, but propulsive damping isn't going to do much, apart from the in the launch, in the first seconds of the launch. So I'm gonna take this part 0, the propulsive damping 0, for this comparison. Okay. So what I did is I took 3 existing rockets. I'm gonna eyeball the specific span, the longitude, the non-dimensional longitude of the nose cone, and I've taken, more or less order of magnitude, the center of gravity, non-dimensional, 0.65, pretty standard. The density of the rocket, I've just taken 650 kilogram per square meter, and I just took 1 kilogram per cubic meter of the air density. So for my eyeball, the specific span of the Hawk is 3.5. For the Rexes is 3, and for the Stratus 3 is pretty low. It's only 2. What about the longitude of the specific longitude of the nose, or let's call it the non-dimensional nose length? For the Hawk, I think it's something like 0.22. Rexus 0.35, and Stratus, it has a small nose compared to the length. Remember, this is like literally eyeballed from what I could see in the internet. But thanks to all this analytical analysis, we can see what order of magnitude we get for the damping ratio. Okay, so the results are the following. Know that the specific span varies quite a bit. The Hawk's fins look really big compared to you know, Stratus 2, which are pretty, you know, thin. So pretty different rockets. However, the results I had are the following. For the Hawk is 0.064. For the Rex is 0.058. And for the Stratus 3, 0.068. Practically the same, the three. You can do tests with different rockets. You can try changing a bit the center of gravity. Always think about, you know, realistic numbers. It's not going to go above 0.8, 0.7. It's not going to go below 0.5, 0.45. I don't know. The specific length of the nose cone, yeah, from 0.1 to 0.4 at most. If you play around with these numbers, specific span, I've seen stuff between 2 and 4. Sometimes it can get slightly off bounds, but it's around that. If you test numbers with, with these different bounds, you're gonna see that you're gonna get damping ratios around this, unless you put a crazy span, or I don't know, you change a lot of some of the variables, but it's always going to be undamped, that for sure. I mean, that for sure. And it's normally going to be really, really undamped. 0.06 is a really undamped system. Okay, so remember, when we have such undamped systems, resonance is going to be catastrophic. There's no way you can survive resonance. The gain is tremendous. So yeah. On the next video, I'm gonna look at the natural frequency, which is probably more interesting. We can get more information. From here we can only know that order of magnitude is going to be similar in different rockets. It's going to be really low. That means resonance is going to be catastrophic. We gotta do our best to not to roll the rocket on the natural frequency, because it's going to blow up. And yeah, that's about it.